Good day, everyone. Today we are going to present to you the Chapter 24 Recent Trends in Mathematics. This presentation is about how mathematics has changed and improved in recent years. It also shows that math is not finished yet and continues to grow as new ideas are discovered. Introduction. This chapter highlights the remarkable progress made in mathematics in recent years, marked by the resolution of long-standing problems and the emergence of new connections between disparate fields. We'll explore four key areas: the four-color conjecture, the classification of finite simple groups, Fermat's last theorem, and the groundbreaking work of Field's medalist. This development showcased the power of human ingenuity and the ever-evolving nature of mathematical discovery. So, when we hear the word mathematics, we often think about numbers, solving equations, and taking exams. However, mathematics is much more than that. In recent years, many very hard problems that mathematicians worked on for hundreds of years were finally solved. This chapter helps us understand how math continue to develop and why it is still important today. So next, the general trends and context. First, period of resolution. The era is defined by the solution of several long-standing, historically difficult problems, some of which stood for centuries. Second, the interdisciplinary focus. There is a strong trend toward unifying previously disparate fields, such as connecting numbers theory with algebraic geometry and topology. One major trend in modern mathematics is solving problems that were once thought to be impossible. Another important trend is connecting different branches of mathematics, such as algebra, geometry, topology, and number theory. Instead of working alone, mathematicians now work together and share ideas to solve complex problems. Technology, especially computers, also plays a big role in modern mathematics. So next, the Fields Medal, a key event that reflects trends awarded every 4 years at the International Congress of Mathematicians, or ICM, to mathematicians under 40 for exceptional achievement. So lastly, key fields as reflected by Fields medals. Research has recently focused heavily on topology, algebra, and algebraic geometry and number theory. So, the Fields Medal is one of the most prestigious awards in mathematics. It is given every 4 years to mathematicians who are under the age of 40. The purpose of this award is to recognize new ideas and encourage young mathematicians to contribute their research. Many important discoveries in recent mathematics are connected to Field Medal winners. So next, the four-color conjecture or the computer proof. This theorem was the first major mathematical theorem to be proved with the essential assistance of a computer, changing the definition of a proof. The first published proof by Alfred Breithkamp, 1879, was later found to be flawed. P.G. Tite also produced a flawed proof shortly after. Heawood's contribution. Percy John Heawood, 1890, discovered Kemp's error and established the five-color theorem, proving that five colors are always sufficient. So the four-color conjecture is a problem about map coloring. It asked whether a map can be colored using only four colors so that no two neighboring regions have the same color. At first, the problem seems very simple, but proving it was actually very difficult. Many mathematicians tried to solve it, but early proofs were later found to be incorrect. So next, the topological link under the four-color conjecture. As I said earlier, the four-color conjecture is about map coloring. It says that any map can be colored using only four colors so that no two neighboring regions have the same color. A mathematician named Hewitt connected the problem to Euler's characteristic concept from topology. The formula is V minus E plus F is equal to X, when V is vertices, E is edges, and F is faces. The formula helps mathematicians understand maps mathematically. So here's the key concept in the proof. First, an avoidable set, a collection of patterns that must appear on any map. And second, the reducibility, a pattern is reducible if whenever it appears, the map can still be colored with four colors. And Kemp chains are used to rearrange colors safely. Third, the charging method, a technique to ensure all possible map patterns are considered and helps prove that the unavoidable set truly covers all maps. Lastly, computer proof and verification. In 1997, a simplified computer proof was done by Neil Robertson, Daniel Sanders, Paul Seymour, and Robin Thomas. They only checked 633 configuration and used exact arithmetic to avoid errors. Later, in 2005, George Gonthier formally verified the proof using the Proof Assistant software, making it completely reliable. So next, the classification of finite simple groups, the enormous theorem. This theorem aims to categorize all finite simple groups, which are the basic building blocks of all finite groups. Similar to how prime numbers are building blocks of integers, a finite simple group is a group that has no normal subgroups except the trivial subgroup and the group itself. The historical precursors, first Évariste Galois, introduced the concept of normal subgroups, which helps us understand the structure of groups. Next, William Burnside conjectured that every non-commutative finite simple group must have even number. Brouwer's program in 1954, proposed by Richard Brouwer, this program classified groups by the centralizer of an involution. Involution, an element that gives the identity when applied twice. Centralizer, all elements that commute with a given element. Phi-Thomson theorem, 1963. Proved by Walter Phi and John Thomson, it states that all groups of odd order are solvable. Solvable means a group can be broken down step by step into simpler groups. This provoked Burnside's conjecture. Fun fact, the proof was 255 pages long. Next, the classification theorem, a massive collaborative effort led by Daniel Gorenstein. Every finite simple group belongs to one of four families: A. Cyclic groups, B. Alternating groups, C. Groups of Lie type, and D is 26 sporadic groups, rare and exceptional. So next, the length and complexity. The original proof is over 10,000 pages, spread across many journal articles. The monster group is the largest sporadic group, with about 8 times 10 to the 53 elements, constructed by Robert Grease in 1982. And lastly, the second generation proof, initiated by Gorenstein, Lyons, and Solomon. The goal is simplify and organize the proof into a verifiable, coherent series of volumes, making it easier for mathematicians to study and confirm the classification. And to conclude, the four-color conjecture and the classification of finite simple groups, both topics shows how mathematics combines logic, creativity, and collaboration to solve incredibly complex problems.
Fermat's last theorem. Pierre de Fermat wrote this statement in 1637 and claimed he had a proof but never showed it. The statement x raised to n plus y raised to n equals z raised to n. Solutions exist for like, but no solutions exist for higher powers. Important progress. Leonhard Euler proved the case for. Ernst Kummer proved it for many prime cases during new ideas in algebras. Fermat's last theorem. Pierre de Fermat wrote this statement in 1637 and claimed he had a proof but never showed it. The statement x raised to n plus y raised to n equals z raised to n. Solutions exist for like, but no solutions exist for higher powers. Important progress. Leonhard Euler proved the case for. Ernst Kummer proved it for many prime cases during new ideas in algebra. The modern name. Modularity theorem. The real breakthrough came when mathematicians connected Fermat's problem to a completely different area of math. The Tanimaya-Shimura conjecture, later called the modularity theorem, states that certain curves called elliptic curves are closely related to modular forms. Gerhard Frey showed that if Fermat's equation had a solution, it would create a very strange elliptic curve. Ket Ribet proved that his curve could not exist if the modularity theorem was true. If the modularity theorem is true, Fermat's last theorem must be true. Final proof of Fermat's last theorem 1994. Andrew Willis secretly worked for 7 years to prove a crucial part of a modularity theorem. He announced the proof in 1993, but a small gap was found. In 1994, Willis and Richard Taylor fixed the gap using advanced number theory. The proof was officially published in 1995, so after 350 plus years, Fermat's last theorem was finally proven correct. Poincare conjecture. This is a major problem in topology, which studies shapes and spaces. The question, if a three-dimensional shape is closed or no edges, simply connected, every loop can shrink to a point. It is essentially the same as a three-dimensional sphere proposed by Henry Poincare in 1904, proven in higher dimensions earlier. Stephen's male dimensions is equal or greater or equal to 5. Michael Friedman dimension is 4. The 3D case was the hardest. Thurston geometrization conjecture and Ricci flow. William Thurston proposed that all 3D spaces could be classified using geometry. If true, it would automatically prove the Poincare conjecture. Richard Hamilton introduced Ricci flow, a process that smooths shape over time like ironing wrinkles out of fabric. Solution by Gregory Perelman, 2002 to 2003. Gregory Perelman solved the problem by improving Ricci flow and handling its singularities or tears or pinches. He publishes work online, not in traditional journals. He famously refused the Fields Medal 2006, the $1 million Clay Millennium Prize. The Poincare conjecture was finally proven. So, in conclusion, these topics show how modern mathematics works. Problem can take hundreds of years to solve. Different fields of algebra, geometry, topology often connect in surprising ways. Collaboration, creativity, and new tools are essential. That's why mathematics is not just formulas, but a living, evolving discipline.